Alright, so in this video we're going to begin with an example which is kind of interesting, slightly evil, but interesting. So, we're going to consider an open bottom cube. Okay, so meaning we have the 5 sides of the cube, just not the bottom. Okay, so top 4 sides. Okay, we have a vector field, great. Let's 3 ways to compute this. Well, we can do it directly. But if you do this directly, you will be crying forever and a day, so we're just going to make a sad face and we're going to cry. Okay? So we're not going to do that. Okay? We could say, okay, well, we could use Stokes' theorem, right? Let me get the apostrophe right. Stokes' theorem. And so then we can say that this is the integral, the closed line integral. Of the vector integral, okay, f dot ds, and well, it doesn't turn out that that is much better because we need to get a parameterization, right? So if we were to parameterize this thing, we'd have x of s and t, and we would say, okay, well, this is going to be maybe s, t, and then I don't even know how to do that, so you'd have to do it for 4 different sides, or for 5 different sides. Not fun. So we're not going to do this. Okay, this is, again, we are crying. And we're crying. Okay. The third way involves a little bit of cleverness. Okay, so we can certainly say, okay, well, if we look at okay, the vector line or the vector surface integral, okay, f dot ds, okay, we can use Stokes' theorem to say that this is the same as the vector line integral over the boundary of f dot ds. Okay, that we can do. Okay, but now remember that the bottom is closed, so really the boundary of the surface is this bottom piece that is shaded in black here that is missing. So I think what we could say is, well, this is going to be the same as the double integral, or the vector surface integral, over surface, and let's call this s tilde. So it's going to be over s tilde of, and then we have, okay, vector surface integral, okay. Because again, the boundary of these two regions or two surfaces are the same. Okay. So then, if I look at this, then I think the parameterization is going to come more easily, because in this case, I know the z component is 0. S and t are both going to be within 0 to 1. Oops. And t. Okay. And then we can find our tangent vectors, right? So ts. Okay, that's going to be 1, 0, 0, and tt is going to be 0, 1, 0. Okay, and then when we cross them, guess what we get? Okay, we just get, okay, ts cross tt is just going to be 0, 0, 1. Okay, and then when we do the curl, okay, we get something that it looks nasty, but it isn't honestly too bad. xz, and then e to the xyz, and then comma minus yz, e to the xyz, and then comma 2x. And then once you parameterize it, what we end up getting is, and I'm just going to put this in here, so we have 0 to 1, 0 to 1, of, and then with parameterization, you get 0, 0, 2s, and then you dot that with 0, 0, 1, and then ds dt. And so then integral of 2s ds da da da, and you end up with, after a bit of calculation, just 1. Okay, so sometimes you can make your life easier by saying, okay, well, the surface that I need to compute is really complicated. Look at the boundary. Is there anything else with that same boundary? And that's where this corollary comes into play. If S1 and S2 are parameterized surfaces where Stokes' theorem applies, and the boundaries are the same, and the induced orientation is the same, then, well, we're just going to say, using Stokes' theorem and really that example that we saw, their vector surface integrals are going to be the same, despite the surfaces not being the same. Okay, so very interesting corollary. Try to make use of it whenever you can to make your life easier.